Okay, so we have a theorem that says that if a function f is continuous over some interval a, b, or if f has at most a finite number of jumps of discontinuity in between that interval a, b, then we can say that that definite integral from a to b of f of x dx exists, and f is integrable over that function a, b. We also have some rules that help us integrate. And so, first of all, if we have some integration where our bound on the bottom is actually a smaller number than our bound on our top, we usually don't like to write it that way, and we can rewrite it as pulling a negative out and switching the bounds in here. And then take the antiderivative. There's one that says if we have an integral and our bounds are the same, so we're going from a to a of f of x, this is equal to 0. And a geographical interpretation over here is see that that width from a to a is 0. And so a width of that rectangle, well, 0 times any height is 0. Number 2, if we have some constant times some function f of x, so like a coefficient in front, we can pull that outside of the integral and then take the antiderivative of the f of x. So pictorially, if we wanted to look at that, so let's say we had some k value, it was 2 times f of x. If you first find the area under this, and then multiply it by 2, you're actually getting this area of what we originally wanted. Number 3, we just did 3. Number 4, the sum and difference. So we had seen this with indefinite integrals. Same thing with definite integrals. If we're taking the integral from a to b of some function f of x plus or minus the function of g of x dx, those are both differentiable or integrable, then this is equal to the integral from a to b f of x dx plus or minus the integral of a to b of g of x dx. And so if you looked at that possibility, oops. So let's say that f of x was just this function in here, and g of x was this function in here. Then adding the 2 would get us up to here. Number 5, if we have some integral from a to b of f of x plus an integral from b to c of f of x, that's the same thing. These are the same bounds. The bound I end at, I'm starting at with our next integral, same function. I can say this is the bound, lower bound of a to my upper bound of c of f of x dx. So if I'm summing these, it's the same thing as summing it from here to here. Sometimes we like to go backwards because if we have area under, if we're trying to find area and our function dips below the x-axis, notice that this, when I look at the height of a rectangle, that's going to give me a negative number. And so knowing this formula is going to be helpful for us if we're trying to find area and part of our graph dips below the x-axis. We can split it up. So number 6 says max-min inequality. If f has a max value of f and a min value of f on AB, then what we can do is bound this interval. This is the same thing as the min value of f times b minus a. And if we look on the other side, the max value of f times b minus a, that length, our integral, that area would have to be in between those two. So if you look at this graph, the min value that graph hits is right here. And so if we looked at the area of the f value where it hits min, this is our width, b minus a. This area is going to be smaller than our integral. If we look at the max value though, so the maximum spot our graph hits would be here, and we found the area of the height with the max spot and the width b minus a. That is bigger than the area of the whole curve. And so we can use the sandwiching to say that it has to be in between these two values. So domination, if f of x is a function greater than or equal to g of x on all of a, b, then we can say that the integral from a to b of f of x is greater than equal to the integral from a to b of g of x dx. And we're saying this if f of x is greater than equal to 0 on ab, then we know that the integral will also be greater than or equal to 0. Okay, so function is higher than another function. Those y values, for all y values, or equal to, then we can say that this area has to be bigger than this area, which makes sense. Okay, so those are rules that we can use to help us, and those are kind of a geographical interpretation of what could be going on. Now let's look at an example where we're going to use those rules that we just saw and discussed. So we're given what an integral is, that the integral from -3 to 0 of g of t dt is equal to the square root of 2. And now we want to look at the integral from 0 to -3 of g of t dt. We talked about, and that was the first rule that we had shown, that if these bounds were swapped, that was equal to the negative of -3 to 0 g of t dt. So this is equal to the negative, well, we know from -3 to 0 g of t dt is root 2. So we get back negative root 2. Well, if you have an integral b from -3 to 0 g of u du, well, if I go in and I have some function f of x, let's just say is 2x plus 1, and I look at this as f of u, this is equal to 2u plus 1. Am I going to get the same thing when I take the antiderivative at those bounds? Because I'm integrating with those that respect to the variable. So I'm going to get the same thing back. It doesn't matter if I'm just changing the variable in here. But this has to change too. So dt, respect with t, du with respect to u. So this is the same thing as this is, root 2. So I can rewrite this using rules. This is the same thing in here. I can pull out, if I wanted to, the coefficient from -3 to 0 of g of r dr. So this is equal to 1 over root 2. And the integral from -3 to 0 of g of r dr, the same thing as the integral from -3 to 0 of g of t dt, which is going to be root 2. So when we do that, this is equal to 1. So I want to look at one more example. Where splitting it up could be helpful. Sorry. I need room. So if you're given that the integral from 0 to 3 of f of z dz, this is equal to 3, and the integral from 0 to 4 f of z dz is equal to 7. And it wants us to find, and we probably only have time to do one, so let me just pull that out. How about from the integral from 3 to 4 of f of z dz? Well, I don't have the integral from 3 to 4. I have the integral here from 0 to 3. So let's just say f of z looks like this. So I have the integral from 0 to 3, which would give me, if I was talking about area and above a curve, this. And then I have the area from 0 to 4. So 0 to 4. But if I want the area from just 3 to 4, I could take the area from 0 to 4, this whole thing, and subtract off the area from 0 to 3, and that would give me what I want from 3 to 4. So let's do that. This is the same thing as the area from 0 to 4, f of z dz, minus the area from 0 to 3, f of z dz. Well, we're given from 0 to 4, that integral is 7, minus the integral from 0 to 3, which is 3. This area bounded between 3 and 4 is going to be 4. So those are some examples, given the values, using those rules to help us find the definite integral. So we didn't finish this section. We'll finish this tomorrow, and then we'll get into that fundamental theorem of calculus and an easier way to go through and do integration